We now start module 1 of chapter 7 and we will discuss canonical forms for linear operators on finite dimensional vector spaces. We have already studied diagonalization in detail and we have learnt necessary and sufficient criteria for diagonalizability of a linear operator on a finite dimensional vector space. And we know that there are operators which are not diagonalizable, which means that we cannot find an eigenbasis for the vector space. Now the question is, can we find a basis which may not be an eigenbasis, but at least the operator can be put in a somewhat simpler form? We will see in this module that Jordan blocks are the blocks which simplify this kind of canonical forms. We will see that if a linear operator has the property that its characteristic polynomial splits in the base field, then it can be put in a spatial form, what is known as the Jordan canonical form. That is what we are going to study in this module. Let V denote a finite dimensional vector space over a field F. Suppose that T is a linear operator on V and that the characteristic polynomial of T splits in the base field F. That means the eigenvalues of T are in F. Let lambda 1, lambda 2 and so on lambda k be the distinct eigenvalues of T. Let us recall that n lambda 1, n lambda 2 etc. up to n lambda k, these denote the eigenspaces of T corresponding to the eigenvalues lambda 1, lambda 2 and so on lambda k. Now we know that diagonalizability of T means that V has a direct sum decomposition in terms of the distinct eigenspaces of T given by V is equal to n lambda 1 direct sum n lambda 2 and so on direct sum n lambda k. So naively speaking, if diagonalizability fails, then some n lambda I eigenspace is small. Let us define a Jordan block. For a scalar lambda, we define the Jordan block denoted by J suffix lambda to be this matrix, where the only non-zero entries would be sitting on the principal diagonal and the upper of diagonal, and everywhere else it is 0. So that means this lambda is sitting on the principal diagonal and then the upper of diagonal has 1s and every other entry is 0. So this is what is called a Jordan block, and we often omit 0 from this expression because it is understood that except for those two positions, the principal diagonal and the upper of diagonal, every other entry would be 0. Our aim is to select an ordered basis B for the vector space V such that the matrix representation of T with respect to this basis B takes this form, where these AIs are matrices and these could be either 1 cross 1 matrix, that means a scalar lambda, or a Jordan block, and every other spot are the 0 matrices. So, it is an expression in block form, and the non-zero blocks are either 1 matrix of the form lambda or the Jordan blocks, and lambda is an eigenvalue of T. Definition: the matrix TB is called a Jordan canonical form of T. We say that the ordered basis B is a Jordan canonical basis for the operator T. And note that Jordan block is almost a diagonal matrix except for that upper of diagonal entries, and TB is a diagonal matrix if and only if each AI is of the form the 1 cross 1 matrix lambda. Let us look at this example. Suppose that T is a linear operator on C8, C is the set of complex numbers, and B is set consisting of these 8 vectors V1, V2, V8 is an ordered basis such that the matrix representation of T with respect to this basis B is the one given here, that is, it has 4 blocks. You can see on the top left corner, that is a Jordan block J1 of size 3, then you have a 1 cross 1 matrix, and then again a Jordan block J3 of size 2, and another Jordan block J0 of size 2. So, this is a Jordan canonical form for the operator T, and B is a basis which gives rise to this Jordan canonical form. So, a Jordan canonical basis. In this block form, except for those 4 blocks, every other entry is 0. Then it is clear that the characteristic polynomial of T is determinant of this J minus Ti, and that is T minus 1 whole raised to 4, T minus 3 whole raised to 2, and T square, and hence the multiplicity of each eigenvalue is the number of times the eigenvalue appears on the diagonal of J. Also observe that V1, V4, V5 and V7 are the only vectors in this basis B that are eigenvectors of T. That is also clear from that Jordan canonical form, and these are the vectors corresponding to the columns of J with number 1 above the diagonal entry. We also note that T of V2 is equal to V1 plus V2, and therefore shifting V2 to the left hand side gives T minus I of V2 is V1, and we have T minus I of V3 is V2, since V1 and V4 are eigenvectors of T corresponding to lambda equal to 1. Now, it follows that T minus I raised to 3 of Vi is 0 for I is equal to 1, 2, 3 and 4. Similarly, T minus 3I whole square of Vi is 0 for I is equal to 5 and 6, and T minus 0I whole square of Vi is 0 for I is equal to 7 and 8. in view of these observations, we can say that if V lies in a Jordan canonical basis for a linear operator T and is associated with a Jordan block with diagonal entry lambda, then T minus lambda I raised to P of V is 0 for some large enough P. Eigenvectors satisfy this condition for P is equal to 1. Our aim is to prove that every linear operator whose characteristic polynomial splits has a Jordan canonical form that is unique up to the order of the Jordan blocks. It is not true that Jordan canonical form is completely determined by the characteristic polynomial of the operator. When we studied diagonalizability of a linear operator on a finite dimensional vector space, we saw that the splitting of the characteristic polynomial of the operator in the base field is definitely a necessary criteria for diagonalizability of the operator, but it is not sufficient. We have seen examples also. On the other hand, when we studied inner product spaces and then adjoint of an operator, then we studied the Schur's theorem, which said that a linear operator whose characteristic polynomial splits in the base field can be put in the upper triangular form. So, that is where we saw a kind of softer form of diagonalizability, well, not quite, but at least it was in the upper triangular form. And now when we are talking about Jordan canonical form, we see that we expect that any linear operator on a finite dimensional vector space V and whose characteristic polynomial splits in the base field can be put in the Jordan canonical form. We will be able to establish this, but then we have to understand that we can have operators with different Jordan canonical forms, but having the same characteristic polynomial. Let us see an example now. Let T dash be the linear operator on C8 such that the matrix representation of T dash with respect to the basis B is J dash, where B is the ordered basis of the previous example and J dash is in the diagonal form, where you see these 4 1s sitting over there, then 2 3s and 2 zeros. All other off diagonal entries are 0. So, here the characteristic polynomial of T dash is clearly T minus 1 raised to 4 into T minus 3 raised to 2 into T square, which is the same as that of T in the previous example, but you can see that the Jordan canonical forms are different. Therefore, we cannot expect that operators with the same characteristic polynomial would have the same Jordan canonical form. We now extend the definition of eigenspace to generalized eigenspace of an operator T, and our aim is to select ordered bases for these generalized eigenspaces, which are subspaces, such that their union form an ordered basis for V and the Jordan canonical form is achieved. So, for diagonalization, we saw that we had the distinct eigenspaces whose direct sum was the whole vector space V, and therefore we selected basis for the eigenspaces, took their union, and that formed an eigenbasis. So, here also we are trying to do something similar, but not with eigenspaces, because the operator T may not be diagonalizable. So, we would be doing something similar with the generalized eigenspaces. Let us first define them. So, definition: let T be a linear operator on a vector space V, and let lambda belong to the base field F. A non-zero vector V in the vector space V is called a generalized eigenvector of T corresponding to lambda if and only if T minus lambda I raised to P of V is 0 for some positive integer P. So, you can see that for P equal to 1, V is in fact an eigenvector for the eigenvalue lambda, provided of course V is not 0. Note that if V is a generalized eigenvector of T corresponding to lambda, and if P is the smallest positive integer for which T minus lambda I raised to P of V is 0, then of course T minus lambda I raised to P minus 1 of V cannot be 0, because P is the smallest positive integer with this property. And therefore, when we apply T minus lambda I on that vector T minus lambda I raised to P minus 1 of V, then we get 0. Therefore, T minus lambda I raised to P minus 1 of V is an eigenvector of T corresponding to lambda, and lambda is an eigenvalue of T. Let us now define what is called the generalized eigenspace of T. T is a linear operator on V, and lambda is an eigenvalue of T. The generalized eigenspace of T corresponding to lambda, denoted by k lambda, is the subset of V defined by set of all those vectors V such that T minus lambda I raised to P of V is the 0 vector for some positive integer P. Now, k lambda definitely consists of the 0 vector and all the generalized eigenvectors corresponding to lambda. Now, a theorem: let T be a linear operator on V and let lambda be an eigenvalue of T. Then 1, k lambda is a T invariant subspace of V containing the eigenspace n lambda, that is kernel of T minus lambda I. And 2, for any scalar mu other than lambda, the restriction of T minus mu I to k lambda is 1 1. Proof of the theorem: 1 is easy to verify. Now, part 2, let V be a vector in k lambda and T minus mu I of V is 0. Suppose that V is not 0. Let P be the smallest integer for which T minus lambda I raised to P of V is 0, and P being the smallest integer, we can say that T minus lambda I raised to P minus 1 of V is not 0. Let us call that vector W. Then T minus lambda I of W, which is the same as T minus lambda I raised to P of V, that is 0, and therefore we get W is in n lambda, the eigenspace of lambda. Furthermore, we have T minus mu I of W is equal to T minus mu I of T minus lambda I raised to P minus 1 of V, and therefore, this is the same as T minus lambda I raised to P minus 1 times T minus mu I of V, and that is 0. So that the vector W actually belongs to n mu, but lambda and mu are different, and therefore, the only vector shared by n lambda and n mu is the 0 vector. So, n lambda intersection n mu is the 0 vector, and therefore, W is the 0 vector, which is contrary to the hypothesis. Therefore, we get V must be the 0 vector. So, we started with T minus mu I of V is equal to 0, and what we finally obtain is that V is equal to 0. Therefore, T minus mu I restricted to k lambda is 1 1. Another theorem, let T be a linear operator on a finite dimensional vector space V such that the characteristic polynomial of T splits in F. Suppose that lambda is an eigenvalue of T with multiplicity m, then part 1 says dimension of k lambda is less than or equal to m, and part 2 says k lambda is precisely the kernel of T minus lambda I raised to m. Recall that k lambda is the generalized eigenspace for lambda. Proof of 1, let W denote this generalized eigenspace k lambda, and let Pt be the characteristic polynomial of the operator Tw, that means T restricted to W. Then we know that Pt divides the characteristic polynomial of the operator T, and therefore, it follows that lambda is the only eigenvalue of Tw. Hence, Pt is equal to T minus lambda whole raised to D, where D is dimension of W and D has to be less than or equal to M. This proves part 1. Now, part 2, it is clear that kernel of T minus lambda I raised to M is contained in k lambda. Now, let W and Pt be as in part 1. Then P of Tw is 0 by the Cayley-Hamilton theorem, because Pt is the characteristic polynomial of Tw, and we know that the characteristic polynomial is satisfied by the operator. Therefore, T minus lambda I raised to D of V is 0 for all V in W. And since D is less than or equal to M, we have k lambda is contained in kernel of the operator T minus lambda I whole raised to M. Therefore, we have proved this inclusion in both ways, and therefore, k lambda is the same as kernel of T minus lambda I raised to M. This proves the theorem. We have defined Jordan blocks. We have also learned what is called a Jordan canonical form, and our aim is to find a suitable basis for the vector space V such that the operator T on V has the Jordan canonical form with respect to that basis. We have defined generalized eigenvectors and generalized eigenspaces, and we will use these concepts to prove that an operator T whose characteristic polynomial splits in the base field can be put into the Jordan canonical form.